Hey everyone, wanted to do a rate law example problem using the technique of determining the reaction orders via experimental data. So this is the textbook example, I believe from section 17.3, so you can go online and check that out. I'm not going to bother to read through all the problem here, but it's simply talking about the rate law of ozone depletion at the poles. So what I'm most concerned about here is the reaction, the chemical reaction, as well as this data. And you can see here that it's given me a specific temperature. The reason for that is that the value of K in my rate law is going to be temperature dependent, right? And so as I'm writing my generalized rate law here, I need to take into a consideration that this value is going to vary depending on what temperature that reaction is occurring at. And so this specific value of K that we're going to calculate towards the end of the problem is going to be valid only at 25 degrees Celsius. Or sorry, yes, 25 degrees Celsius. So that's an important thing to know. All right, so I've written my generalized rate law here based on the products in my chemical reaction, and my first step is going to be to determine the values of those reaction orders, the exponents in that expression. All right, so I'm going to start with M first. And what this is telling me, what M, this value is telling me, is how when I change the concentration of nitrogen monoxide, how does that actually impact the reaction rate? And I'm actually measuring reaction rate by measuring the concentration of nitrogen dioxide over time in molar per seconds. And so if I really want to understand how changing nitrogen monoxide concentration changes the rate, I have to isolate that and keep everything else constant. And so I have one additional reactant. And so I have to look at the trials where that second reactant is held constant so that I can isolate the impact of changing the concentration of my first reactant, nitrogen monoxide. So I'm going to look at my second column here, and I'm going to see that these three trials right here have the same concentration. So that means that I can look at those three trials, 3, 4, or 5, to determine the impact on changing nitrogen monoxide concentration. So I just have to pick 2 of those, but you can pick any 2, 3 and 4, 4 and 5, or 3 and 5. You'll get the same response. Okay, so what I'm going to do is I'm going to set up a proportion. You can do this in your head, but I'm basically looking at how I change this and how this changes. So I'm going to divide. I always put the bigger number on top just because I sort of like having whole numbers instead of fractions. And I can do this in my head. I can look and see that 1.0 times 10 to the minus 6 and 2.0 times 10 to the minus 6, I'm doubling this. But if the numbers aren't as straightforward, you can simply divide them. And I'm leaving units off here. All right, so that's going to be equal to x. I'm going to let that equal x. And then I'm going to put my rate over here. So I can't quite do that in my head. I mean, I can sort of like eyeball that and see that it's about 2. Sorry, I'm writing over my. All right, so I'm going to plug that in my calculator. This value equals y. So this one we said is 2, and when I verify this one, this is also 2. So now what this means is when I double the concentration, the rate also doubles. And so that dependence is going to follow the formula 2 to the m, which is my reaction order, equals 2, or 2 to the, sorry, x to the m equals y. All right, so this is this, and this is this. And so I know that 2 raised to the first power is going to equal 2. So m is equal to 1. So now I can go ahead and substitute this into my rate law as a 1. All right. So that's my first step. Now my second step is going to be doing the exact same procedure for my second reactant and determining the value of N. I'm going to do this one right now. So now, since I'm doing the impact of ozone, now I have to look at which trials am I holding nitrogen monoxide constant? And I can see that these three trials, 1, 2, and 3, I'm holding that reactant constant. So now I'm going to analyze these three. All right, so I'll just do 1 and 2. All right, so I'm going to look at 6.00 times 10 to the minus 6 over 3.00 times 10 to the minus 6, and I can see very easily that's doubled. And then I'm going to do this one. Right, so this one is right here, times 2. I'm not so sure about that, so let's take a closer look with my calculator. 1.32 times 10 to the minus 4 over 6.60 times 10 to the minus 5. So you just plug that into your calculator, and you'll see that this one is also 2. Now remember, these exponents are not the same, so you cannot make that same assumption that I did here. But I did plug that in my calculator before and got that was a 2. So it's pretty obvious that I have the same expression here. So I know that that reaction order is going to be the same, but you would do this every time. So this now is equal to 1 also. So I'm going to substitute this guy in here. And so that's my reaction orders. So once I've determined my reaction orders, my last step is to determine the value of K. Remember, K is dependent on the temperature as well as the chemical reaction that you're running. And so we're going to use trial 1 data. Just drop down here. I'm going to drop those 1s because anything raised to the first power is itself. And I'm simply going to use this trial's worth of data, everything in that row. And I'm going to plug it into my rate. All right, so let's see, the rate is 6.60 times 10 to the minus 5. And the unit here is moles per liter per second. So that's molars per second. And we're trying to find K, so that's my unknown. And my 1.00 times 10 to the minus 6 and 3.00 times 10 to the minus 6. Both of those are molar. And remember, these are raised to the first power. Okay, so I'm simply going to divide both of these by this product to isolate that on K on its this side. Oops. All right, and so this cancels obviously, and so now I'm left with K, and the answer I get to 3 sig figs is 2.20 times 10 to the minus 7. And now I'm left with determining my units. So let's kind of highlight these in a different color. Actually, let me hurry this up. There we go, there and there. All right, I'm gonna draw these in red so it's a little bit easier to, I'm gonna stick that per seconds right down here. All right, because that's what that is. All right, so now I'm just gonna cancel. I have 1 molar here and 1 molar here. So when this kind of goes away, I'm left with a 1. And so my unit is gonna be 1, and what I'm left with here, molar seconds. And that's the unit of K. That's for this one. So my overall rate law, again, this is the expression that defines the reaction rate regardless of concentration at 25 degrees Celsius. So I'm going to leave the rate is equal to my value of K that I just determined with the units. And then I'm going to leave these concentrations also blank so that I can plug anything I need in there. So regardless of the concentrations I have, I could determine the rate with those concentrations. And that is my rate law. That's how I do that.